to concentrate on this BRST method. So in the first lecture, and I'll review it in the first part of this lecture, I discussed how to do this for the bosonic, first for the particle and then for the bosonic string, and today we'll do the spinning particle and string, which is also the RNS version of the spinning particle and string. And then in the third, tomorrow I'll start doing the space-time supersymmetric version, which is called superparticle. So I'll do it first with what's called Brink-Schwarz, or the Green-Schwarz version, and then with pure spinor. So probably this will take 2 lectures. And then we'll do the superstring. So all of this will be discussing just quantization. And then in the last lecture I'll discuss applications. Okay, so this last lecture will be more descriptive. So amplitudes, curved background, so ADS5 times S5. So I think this will be more pedagogical, and I hope everybody will be able to follow, at least until it gets to be more descriptive. So the idea is to ask questions. So when you stop asking questions, that means people are lost. So just keep asking questions. Okay, so I don't know if there are any questions from yesterday, but the first part of this lecture will be review. So as I review the things from yesterday, ask questions if there was something you didn't understand. Okay, first of all, I gave an exercise. Were there any problems or questions about doing the exercise? Okay, so perhaps what I should have done yesterday was start by the general BRST method and then do the specific cases. Okay, so the way I did it, I started with the specific cases. But the general cases, you have let's suppose we just have bosonic coordinates. So we have these d-dimensional coordinates, and you have some constraints. And let's suppose they're all first-class constraints. So we work in the Hamiltonian formalism, so we have x's and p's. And in the Hamiltonian formalism, these constraints can involve x and p, but they don't involve time derivatives of x and p. Okay? So x and p satisfy the usual commutation relations, I guess minus I delta mn. So I set h bar equal to 1. And then you can show that if these are first-class constraints, they generate gauge symmetries. So the gauge symmetries are generated by commuting G. So this would be, I made it like this. So for each constraint, I have a gauge symmetry. So J goes from all over the constraints. So J, let's say, goes from 1 to n. So this would be the gauge transformation of x. Gauge transformation of p would be similar. So all of these means the usual canonical commutation. So if we're doing Poisson brackets, you can interpret it that way. So I'm not being careful, but of course if you want to be careful, you have to worry about normal ordering and all the usual subtleties when you do quantization. So if these are first-class constraints, what it means that when I take the commutator of G with itself, or 2 G's which are different, I get another G. So that's the definition of first-class constraints. And these F's are the structure constants from the Lie algebra of these constraints. Okay, you can consider more general systems where these F's can depend on x and p, but I'm not going to do that here. Okay, so in this case, let's suppose that these are really constants. They're just structure constants of some Lie algebra. Okay. Okay, so if you do this, you find the action is only invariant if you also transform E. So E are these Lagrange multipliers. So again, up to science, I haven't been careful, things like that, but I think this is something like minus I epsilon dot. So the dot comes from this transformation here. That's the only place d tau comes into the game. But then you also get contributions from the transformations of G. So the transformations of P and X from here is going to be cancelled by this, but the transformations from G is going to mean that you have another term which is of this type. Okay, so this is completely general in the sense that I haven't told you what the G's are, I just told you the algebra, but it's easy to show the action is invariant up to a total derivative with these transformations. Okay? So that's the general case. And now if you want to gauge fix, of course there are different ways you can gauge fix, but one way to gauge fix is to fix the E's to be constants. Okay? So for each E you have a gauge transformation, and the gauge transformation involves a time derivative, so that means the ghosts coming from this gauge fixing is going to propagate, So you have Fadeev-Popov ghosts. So let's suppose we fix Ej to be just some fixed values. So let's call the fixed values, I don't know, Hj. Okay? So these are just constants. Okay? So you can ask, well, I could set them to 0, but as I told you, sometimes setting them all to 0 is singular. So we don't want to, we may want to set them all to 0, but we don't have to. Okay, so in that gauge, of course, you just get Hj here, but then you get ghosts. Yes? How did I get this? So you're asking me why I defined it like this? It's okay? Okay, any other question? Okay, so you also get ghosts. So the way the ghost transforms, the way the ghost appears in the action is related to the gauge transformation of E. So you'll get the term minus I C dot J minus C K F J K L, and now we just set E equal to H. Okay, so this is the gauge fixed action. And gauge fixed action means that, of course, we've broken these gauge symmetries, but there's still a global symmetry left over, which is just the BRST symmetry. So there's a global gauge symmetry, there's a global symmetry, which is, if you compute the Noether current, it's just a BRST charge. So what you find is that this action here, if you do these transformations and you replace by epsilon c, so these are the usual BRST transformations, you find that the BRST operator is just Cj Gj plus so again, I'm not being careful with normal ordering, and of course when you do the complete quantum theory you need to be careful. Okay, so this is the Noether charge for the global symmetry. Okay, so this is the, and of course this is anti-commuting because these ghosts are anti-commuting. So this is the general BRST method for quantization. Okay, so this, of course, you can now consider specific cases. So are there any questions? Okay, so now let's just review what we did yesterday for the different cases, and if something wasn't clear, just stop me. Okay, so the first case we did was just the relativistic particle, so that was just E times P squared. And then we chose the gauge E equals, let's say, half. So then this just becomes after using the equation of motion for P, this just becomes x dot squared. But then you get a set of ghosts. You just B times C dot. And Q is just equal to C times P squared. Okay. And then we computed the cohomology. So V, the vertex operator, or the states in the cohomology can either depend on X or on C. So we wrote these as two fields. Let me call it phi 0 and phi 1. I called it phi and phi star, but just to let me write it with a subscript here, which just tells you the ghost number. So C, of course, has ghost number 1, and B has ghost number -1. And then QV equals 0 implies box phi 0 equals 0. And delta V equals Q of omega implies delta phi 1 is box of omega. So it implies that you can gauge away phi 1 unless box phi 1 equals 0. Okay, so this describes the usual massless field, and this is what's called the antifield. So you get this doubling, which is essentially always appears in this BRST quantization. Okay, any questions about this? So if you have any questions, this is the simplest case. So yeah. Gauge away phi 1. So delta phi 1 has this form. So only if box gauge away, gauge to 0, gauge away. Gauge away means you can remove it by a gauge transformation. So that means the only thing that remains after you compute the kernel over the image of Q is the only states in this are phi 0 and phi 1, where both of them satisfy box. Okay, so really for anybody, this is for everybody. And obviously as we go through the list of things, some people are going to start to get lost. But at this stage, everybody should be able to follow what's going on. So are there any questions? Yes? Yes. Yes, that's right. So C is anti-commuting just because in the usual BRST, the ghost is always the opposite statistics from the Lagrange multiplier. Okay, so the next thing was the string, bosonic string. So in that case, this is slightly more complicated. Yes? So the BRST so C is defined to have ghost number 1. The BRST operator is ghost number 1. The physical states, that's not clear exactly which are the physical states, if that was your question. But the fact that C has ghost number 1, that's by definition. I don't know which part was your question. I define it to be ghost number 0 because there's no ghosts here. Well, because this, because this term here has ghost number, well, okay. I guess it's so C has ghost number 1. So probably I should have called this ghost number -1 then. Okay, so the total V, let's say, has ghost number 0. Okay, so there's some ambiguity in what one calls ghost number, but normally one calls these ghost number 1 fields. But okay, maybe it's the correct term would be ghost number -1. Right. Yes. That's right. So if box is, let's suppose we diagonalize box. So if box has 0 eigenvalue, then of course box phi 1 is also 0. So. Any other questions? Yes. So capital omega is a gauge transformation, which I could also write in this form if you like. It's a gauge parameter. So this omega here. And your question was? So it's just a field here which depends on x, which I think of as a gauge parameter. Just like in Yang-Mills, you have delta A mu is d mu of lambda. It's the same thing as this lambda. So it's a gauge parameter. And the transformation of the field depends on that gauge parameter. And of course, if you can gauge it away, then there's nothing left over in this cohomology. If you cannot gauge it away, then it's physical. Yes? Okay, so in some sense they're related to each other, but the way I'm defining omega is in this way here. So V is my physical states, or these states here, and the transformation of the BRST transformation of V depends on this omega. Okay, so they're complementary in some sense, but okay, but this I interpret as the gauge parameters, and these as the physical states. So I didn't hear so omega is the gauge transformation, is the gauge parameter. And delta V is the gauge transformation of V. Okay. Yes? That's the definition of the gauge transformation of V. Okay. So as I said, that's the physicist way of interpreting this cohomology. So physical states are given by equations of motion up to gauge transformations. So for example, if I look at Maxwell's equations, the equation of motion is F Mn dm is equals 0. So that of course has the usual solutions for Am. And this equation would naively tell you that there are 3 independent degrees of freedom for a photon. But you always have to divide this by the gauge transformation, which is delta m equals dm lambda. So although this gives you 3 solutions, this one reduces it to the usual 2 photons. So the longitudinal photon is eliminated by this one. So that's how the physicist interprets this cohomology. It's the equations of motion. So the equation of motion is QV equals 0 up to gauge transformations. So these are the gauge transformations. Yeah. No, it's this local field. So lambda, this is a function of x. So you divide by the usual local gauge transformation. So that's the way one interprets this delta V equals Q of omega. So you're right. In the first quantized formalism, there's a global gauge, global BRST symmetry. But the global BRST symmetry encodes the local, the second quantized, if you like, gauge symmetries. So there's a question here, yeah. from the p squared. It's no double pole. It's just we're just doing quantum mechanics. So p squared is just d dx squared. Huh? There's no dc. This is just quantum mechanics. So this is just c d dx squared. So p is just d dx. So okay. So when you yes. Yeah. So for what we do in field theory, we never think about these anti-fields. When you discuss more complicated methods for quantization or quantization of systems that are more complicated, sometimes these anti-fields play a useful role. So this is, if you want to read about this, this is Batalin-Vilkovitsky quantization. So there's a whole method of discussing renormalization and other techniques in quantum field theory where it's useful to introduce anti-fields, and you have a mastery equation and things like that. But for these lectures, the only thing you have to know is that the cohomology is typically doubled, and so this field will appear actually twice. Yes. So if you have electromagnetism, the gauge field has 4 components. If you impose the equations of motion, it turns out that one of those 4 components drops out. Yeah. So if the equation of motion kills one of those components, and the gauge symmetry kills another one. Yeah. So right now I'm just doing quantum mechanics. So when we do the string, then yes, these vertex operators, when I use to compute scattering amplitudes, will be related to state operator correspondence. But at the moment I'm just computing the spectrum. So yeah, you can think of this as a wave function if you like. So instead, vertex operator is just a word. So you can think of this as just solutions to, it's just usual quantization like you learn in first year of quantum mechanics. So you have psi of x. It doesn't satisfy Schrodinger equations. It satisfies something more complicated. It has to be annihilated by these constraints. So I should say all of this is, not all of this, but most of this is discussed in Dirac's little book called Quantum Mechanics. So how to quantize constrained systems, yeah? No. So if you want to do BRST quantization, you have to be able to define this. So the physical states have to have this kind of property. And in order to make sense out of kernel of Q over imaginary part of Q, you have to assume, of course, that the imaginary of Q is a subgroup of the kernel of Q. So that's only possible if Q squared equals 0. So if Q squared does not equal 0, this doesn't make any sense. So you can have Q's which are classically satisfy Q squared equals 0, but because of normal ordering subtleties, they don't satisfy Q squared equals 0 at the quantum level, and then you get anomalies. So that's what fixes the dimension of the string, for example, to be 26. But yeah. Okay, so ghost number, so when you have this BRST method, each Lagrange multiplier gets replaced by a ghost, which has ghost number by definition plus 1. So that means C has by definition ghost number plus 1. So the momentum conjugate to C by definition has ghost number minus 1. And that's essentially the definition of ghost numbers. So. Other questions? No? Okay. Okay, so now we do the string. So the starting point is this. Now we're going to gauge, let's do first conformal gauge. So first gauge, conformal gauge. We gauge all of E and all of E bar to be equal to 1. So E is of course a function of tau and sigma. So P and X are a function of tau and sigma. X prime means dd sigma of x. So we gauge all of E and E bar to be 1. So this implies that the action after plugging this in here and solving for the equation of motion for P, you just get dxm d bar xm, where d is dd tau plus dd sigma d bar. But then you get ghosts. So the ghosts come in this form. So we have two sets of anti-commuting ghosts because we have E and E bar. And if you go through the algebra of these constraints, you find that it's not just B times C dot, because there's some non-trivial dependence coming from the structure constants, which turns the dd tau into a dd tau plus dd sigma. Okay? And Q is now equal to d sigma of C times, let me write it in this form. So this is the BRST operator. And now we can, again, compute the cohomology. Okay? But before we compute the cohomology, which is going to be slightly more complicated than this description here, let me do the light cone gauge fixing. Okay? So light cone gauge fixing, the cohomology is essentially what you already saw in our glucose lecture. So let's do that here. So light cone gauge. We're only going to set the zero mode of E and E bar to be equal to 1. So what does that mean? That means that d sigma of E so then the sigma dependent part we won't try to gauge to 1. We'll use that dependent. So of course we have this sigma dependent epsilons. So we're going to use that to fix dd sigma of x plus and dd sigma of p plus to be equal to 0. So this is a light cone gauge. So in this gauge, p plus is just going to be equal to its zero mode. So I'll just call it zero mode p plus hat. Okay, so this is independent of sigma. Okay, and similarly x plus, it's just x plus hat. Okay, so if you do that, this expression will simplify. So the transverse components will still depend on sigma. Okay, you'll have E times so let's write this. Okay, I'll keep that. But then you have the zero modes only the zero modes of p plus and x plus contribute. So because of that, also only the zero modes of p minus and x minus contribute here. That's just because if only the zero mode of this contributes, then when you integrate over sigma, only the zero mode of this contributes. Okay? So that for the transverse components, all of the sigma dependence is still there, but for the plus and minus components, only the zero mode contributes. And here, you have to remember that the zero modes of E plus and E minus are fixed to 1. Okay? So Q is going to be equal, so you still have some ghosts here. The ghosts also, only the zero mode contributes. There's no plus. All right. So these zero modes of the ghosts come from this gauge fixing here for the same reason as before, Because remember, E transforms with the derivative with respect to the epsilons. Whereas these don't transform with derivatives. Okay? The transformations of x plus and p plus don't involve the time derivative when you compute their gauge transformations. So you only get ghosts from this part. So this part of the action only involves sigma 0 modes. Okay? Where this part of the action depends on all of the sigmas. Okay? Any questions up to now? Yes?
How do you see at this level that I have the one graph in the first line is a gauge fixing condition?
Okay, so you have, remember we have the epsilon of sigma and epsilon bar of sigma. Those are my gauge parameters. And now what you have to check is that you've successfully gauge fixed these symmetries. So epsilon of sigma has, of course, the part which depends on sigma and the part which doesn't depend on sigma. So epsilon of sigma, you can expand in, of course, epsilon 0 plus epsilon n e to the in sigma, sum over n different from 0. So the 0 mode part of it, I'm going to use to fix this to 1. The non-zero mode part, I'm going to fix either x plus or p plus. So, of course, these will fix x plus plus p plus, and the epsilon bar ends will fix x plus minus p plus. So at least I have the same number of gauge fixing conditions as I have parameters. If you want to see another way to see why this gauge fixing is enough is to look at the Fadeev-Popov action. So if the gauge fixing was incomplete, you would find that the Fadeev-Popov action was somehow singular. Okay? So in this case, it's not. It's just a simple action for the ghosts. Okay? Any other questions? Yes. Well, it's C and C bar, but just the 0 modes of them. So you have 2 ghosts and 2, if you like, anti-ghosts. Right. So it's the same like here. Here we had just a C, but now you have a C and a C bar. So yeah, so it gives ghosts, but the ghosts don't propagate. So they don't propagate just because when you look at the gauge transformation of x plus and p plus, you find it doesn't involve time derivatives. Any other questions? Okay, so what is Q? So Q is just, because the ghost is just these 0 modes, what you'll find that Q is just C hat. So hat just means that it's just a 0 mode, remember? Times d sigma of p plus x prime squared plus c bar hat. So you get the constraint, but you just get the 0 mode of the constraint. So there's just a single c hat. So of course, this is just a single constraint. So there's no possibility of a Lie algebra just because it's only one constraint. So it obviously commutes with itself. Okay. So it's different from this case. Here you have the constraint here depends on sigma. So here, of course, you can have non-trivial commutators between this constraint at different values of sigma. Here it's only the 0 mode which appears, so there's nothing else in Q. Any questions? Okay, so now let's look at the cohomology. So here, let's just do the open string. So for the open string, C hat is equal to C bar hat. Okay, and so I really only have to look at Q. Okay, if I was doing the closed string, it would be slightly more complicated. Okay, so V is going to be a function of C hat and, of course, of the xj's, which can depend on sigma. and the zero modes, which are just x plus and x minus hat. Okay? So those are the degrees of freedom. And now we can expand it. So let's call the first phi 0 is just the terms which are independent of c hat. So this just depends on xj. And then you have a term plus c hat. Okay, now we're going to write xj. I guess I don't need this anymore. So we're going to write xj as the zero mode plus, of course, you have the terms n different from 0. Let's write an e to the in sigma. So actually it's cosines and sines. I'm not going to worry about these things here, but I'm going to say that the positive modes, ANs, there's a J here, let's call it capital N, not small n. When capital N is positive, it's a creation operator. When capital N is negative, it's an annihilation operator. So we're going to define a ground state such that AN equals 0 when N is negative. Okay. So my states here can be constructed in terms of this ground, if you like, okay, let's call it ground state, by hitting with A's with N's positive. So you have A and J. So these are my states as far as the dependence on xj. Okay. Then, of course, I can also have dependence on the x hats. So it depends on all 26 of the x hats from in 26 dimensions. So I'm going to write that in this form. Okay, so this would be my general state. I have some momentum k that appears with the zero mode like e to the ik dot x. And then you have some product of these creation operators acting on some state. Okay. So I assume that Augusto used some similar notation, or? Okay. So these will be these phi zeros. And now, since Q has this form, you can show that Q is equal to C hat. If you just take the zero mode part of this, so there are different contributions. This is equal to P plus X prime 0 squared plus P plus X prime N P plus X prime minus N, right? Sum over N different from 0. So I just separated out the zero mode part from the non-zero mode part. Okay. Now the zero mode part, of course, this just is going to give me just k squared. So if we call this V, so this is actually just one state in V. Okay. Obviously, V has all different states depending on what these capitals M's are. But this is a possible V. And then QV equals 0 is going to give me an equation that tells me that this operator acting on that, which is just going to give you k squared, is related to this object acting on it. So what you'll get is you'll get an equation which is k squared plus this object acting on this using the commutation relations of the A's is just going to give you the sum of J of M and J times N. So depending on the mode number, you'll get the contribution of capital N from each of these A's, and then you have this number for each mode number, so that gets multiplied by how many A's you have. Okay. So this is the equation of motion. Yep. Yes. This goes over all of them, because remember the zero modes here are still in the game. Okay. Any other questions? Yes. Good. So, okay. So you asked a good question. So, what happened to the non-zero modes of x minus? Okay. So if you look at this action here, the non-zero modes of E are also still in this action, right? Because we haven't gauge fixed. We only gauge fixed the zero mode of E. We didn't gauge fix the non-zero mode of E. Okay. So the equation of motion. The equation of motion for E, if you take this, is going to imply the derivative d sigma of p plus x prime squared equals 0. And with E bar is going to give you d sigma. You might think it's this. I'm taking the derivative of the Lagrangian with respect to this Vierbein. So remember, we haven't gauge fixed all of E to 0. So it's still in the action. And I'm going to vary with respect to that, and that gives me an equation of motion. The equation of motion is just, it looks like it's just, well, it's all the non-zero modes of this. So for n different from 0. Those are the equations of motion you get from varying the non-zero modes of E. That's the same thing as saying that d sigma of this is 0. Okay? Because d sigma, of course, just kills the zero mode. So anything which is not the zero mode has to vanish. Okay? So this is an equation of motion. And this is going to fix for me x minus and also p minus. So the reason is because this object here, this is equal to p minus of sigma plus x prime minus of sigma times p plus. Remember, p plus just has a zero mode. So when I take the sigma dependent part of this in the longitudinal directions, I just get this. And this has to be plus x prime. So this has to be equal to 0. So what that tells me is that d sigma of p minus, or actually d sigma of p minus plus x prime minus, is fixed in terms of the transverse degrees of freedom. And similarly, from varying E bar, you'll find that d sigma of p minus minus x prime minus is also fixed in terms of the transverse. So that means that p minus, or more precisely the non-zero modes of p minus and the non-zero modes of x minus can be expressed in terms of the other variables. Okay? So from the equations of motion, they're not independent degrees of freedom. And these equations never involve time derivatives, so they can be set to 0 without losing information. So it's what's called an auxiliary equation of motion. Yes? Here? Because remember, x plus, the sigma derivative of x plus is 0 in light cone gauge. Okay? So in light cone gauge, x minus and p minus, at least the sigma independent parts, the sigma dependent parts of p minus and x minus are not independent. They can be expressed in terms of the transverse. Okay? Okay, so we just have dependence on the xj's here. And of course on the zero modes of these. Okay, so this is the equation of motion we get. And this is just the usual light cone spectrum. So we find that the states are just described by these states here, where k squared has to satisfy this equation. Okay. So for example, the tachyon state is just the ground state e to the ik dot x. So this would be the tachyon. And the gluon would just be the state a1 j e to the ik dot x. So this gets written in terms of just aj of x. Let me do it with a little more space. So here we have e to the ik dot x a1 j of x. See? That is written as the state a j of x dxj. So what I've done is I've taken this e to the ik dot x and I've written it in terms of coordinate language. So you can think of this as just the gluon gauge field multiplied by the operator dx. Dx is just this a1j. And in the case of the tachyon, you just have e to the ik dot x, so that goes into this t of x. Okay, so this is how the states are described in light cone gauge. Okay. Okay, sorry. Very good. There's something that I didn't say, which will become clear when we do the covariant quantization, is that there's a normal ordering ambiguity in defining this. And in fact, the correct equation is this thing plus 2 or plus 1 equals 0 if we're doing open strings. So for t of x, you'll find k squared is equal to minus 1. And for this one, you'll find k squared equals 0. Okay. When we do the conformal gauge, you'll see exactly where this comes from. Okay, any other questions? Yes, so far I described the just the phi 0. And now if I want to describe phi 1, what you'll find is there's precisely the same number of states. So if I just act with all of these states here by adding with a c hat, you'll find that the cohomology is the same. So you'll get, for each of the tachyon, you'll get another field. For the gluon, you'll get another field, etc. Any other questions? Okay, so now what we want to do is to get this covariantly. Okay. So here there's a gluon. So you could have asked, well, this gluon, what happened to the gauge transformation of the gluon? So I told you before that the image of Q was supposed to describe the gauge transformations. So I even gave you that example. I said the gluon is supposed to transform like delta A J is equal to dj of something. Well, it turns out in light cone gauge, these gauge transformations are not present. And it's because this A doesn't depend on all the degrees of freedom, right? So if you were in 26 dimensions, you would expect A to have 26 components. Here it only has 24 components. And the reason is because we've already done gauge fixing here. So when I do this light cone gauge, the reason why it's called light cone gauge is precisely because the fields that you get here only have, so the gluon, for example, only has 24 independent components. So you've already gauge fixed A plus to be equal to 0. If you want to do things covariantly or in other gauges, then you can't use this light cone gauge. Okay? So light cone gauge doesn't give you the theory in some gauge covariant way or Lorentz covariant way. Okay? That turns out to present complications when you want to describe interactions, but to compute the spectrum, it's the simplest way because you don't have, I mean, if you want to compute the spectrum and you have gauge symmetries, then you always have to worry about if the theory can be, if certain fields can be gauged away. In light cone gauge, it's extremely simple to analyze the spectrum. So the answer is just this. Okay. So now let's do the conformal gauge. So any questions about this? So Q of so there's nothing you can write down just because the most general state is this. So this is automatically gauge invariant because there's nothing of ghost number -1. Yes? Yeah. Yeah. So, as I said, omega is the gauge parameter, and V are the physical states. Yeah, like the gluon transforms like a gauge field. So the gauge parameter is not the gauge field, but the gluon is. So in this case, these fields here, they don't transform under gauge transformations. Because this AJ of X is gauge fixed. There's nothing, there's no gauge transformation left over in light cone gauge. When we do things in conformal gauge, you'll see that this actually does generate the usual gauge transformations of Yang-Mills. Okay. Any other questions? Okay, so now let's do conformal gauge. So this will make things more interesting, more complicated, but in some sense more useful when we want to understand, for example, what the meaning of these gauge transformations are. Okay, so now we're going to go back to the gauge E equals E bar equals 1. So now Q is this more complicated object. And V now can have much more complicated dependence. So V, of course, can depend on C and X, all the X's. And it can also depend, let's just do the open string, so we forget about C bar and B bar, but it can also depend on B. So these all have modes. So we have to decide which of these modes are creation operators and which modes are annihilation operators. So for X, we already did it. It's like in light cone gauge. So we have XM. So let's say X hat is a 0 mode. And then the creation operators, we'll call them ends with positive. Okay. So this would be multiplied by. So let me tell you what I mean by Z. So before we were describing the states in terms of sigma. So we had e to the in sigma. So the general state would be xm is equal x hat So this is in the coordinate system where we have a cylinder, and sigma is this periodic direction. So it will be convenient to do a conformal transformation to the complex plane. And the transformation is that rho is equal to tau plus I sigma if we work in Euclidean space. Where the transformation to the complex plane is rho equals log z. So when tau goes to minus infinity, it goes to z equals 0. And when tau goes to plus infinity, z goes to infinity. So the different circles here are mapped to circles in the complex plane. Okay. So obviously I can write this in terms of the z coordinates, and what you'll find is that this is just equal to z to the n, a n n. And what we're going to do is we're going to define the creation operators to be n positive, so that this is well defined when z goes to 0. Okay, so if I think of this as a function of z, then near z equals 0, when this acts on the ground state is the thing that's annihilated by all the a's with n negative, this is a regular function. Okay. There's also z bar dependence. I'm just if I'm doing the open string, I can ignore the z bar dependence. Yes? So, right, so actually there's a tau here, and since I'm only looking at the sigma dependence, I've fixed the tau dependence. But when I use the equation of motion, then sigma always appears in the combination sigma plus tau or sigma minus tau. Any other questions? Okay, so that's the x dependence. So what I really want to do is to write this in functions the ANs, where n is greater than 0. Now what about the b's and c's? So this is a function of all of these. I haven't told you which are the coordinates and which are the momentum, or which are the creation operators and which are the annihilation. So with my relativistic particle, remember I only had the 0 mode of c and the 0 mode of b. So I chose the c to be the coordinate and b to be the momentum. I could choose all the c's to be coordinates and all the b's to be momentum, but that's not a very smart choice. So we'll see why in a second. So what we want to do is we want to choose some of the c modes to be creation and some of the b modes to be creation and the others to be annihilation. So naively, you might think you want to define c of z to be equal to c0. So this and you choose all the positive n's to be creation operators and the negative n's to be annihilation. That turns out to be incorrect. And the reason is because, as I mentioned yesterday, C has conformal weight. So when you do a conformal transformation, so let's say Z goes to Z prime of Z, it turns out that C of Z prime is equal to so in general, this could be some number h, which is called the conformal weight of C. In the case that we're discussing, the B and C ghosts where they come from here, this turns out to be -1. So to derive this, the simplest way to derive it is to look at the transformations of the Lagrange multiplier under the constraint, and that's going to tell you also how the B and C ghosts transform under these constraints. So these constraints are the generators of these conformal transformations, these transformations of this type. So of course they're the infinitesimal version. So if you take the infinitesimal version of this, what you'll do is you'll reproduce the infinitesimal transformation of the Lagrange multiplier. Okay, so what you find is that this object has what's called conformal weight -1. So an easy way to see that is from the BRST operator. This object turns out to be, when you use the equation of motion, this object here is just dx squared. So dx, if x has conformal weight 0, dx has conformal weight 1. So this has conformal weight 2. And in order to have the BRST operator be conformally invariant, the total conformal weight of this has to be +1. To cancel the conformal transformation of d sigma. So if this has conformal weight +2, this has to have conformal weight -1. So that's another way to see that the C ghost has to have conformal weight -1. Similarly, the B ghost has to have conformal weight +2. So that means there's a 2 here. And that comes from the fact that if you look at this term, for example, or if you look at this term, if this has -1, this has to have +2 in order that the total conformal weight is, well, +1, +1. Okay, so it's some algebra to show that this actually, the infinitesimal version of this reproduces this, but I'm not going to do that here. But what that implies is that this is not quite right. So if you start in the cylinder, we can define C of sigma to have the obvious mode expansion. But when you do this conformal transformation, because d rho dz is equal to 1 over z, you pick up an extra factor of z. So what you find is that instead of starting like this, you find that C of z starts like this. So you'll get, just write it out, you'll get C0 times z plus C1 times z squared, etc. So it doesn't start at C0 like the x, it starts at C minus 1. And similarly, what you'll find is that B of z, instead of starting with B0, it starts with B2, then you get B3z plus etc. Okay, this mode number is going to be relevant because when we compute the mass shell condition, you'll find that the C ghost contributes a negative sign. So in fact, this -1 here is precisely the same as this plus, I mean, if I wrote this equals -1, then this is the same -1. Okay. So it turns out that the mass shell condition now, if you include the contribution from the BC ghosts, so I don't know what we call it, M prime, so this will come from the BC ghosts, the total sum is equal to 0 now. Sorry, that's right. This is now the total, goes from 0 to 25. Okay, so let's see how it works. So we have these B's and C's, we have these A's. Now the covariant vertex operator is going to depend on all of them. So it depends on B2, B3, depends on C minus 1, C0. It depends on all the A's, so yeah, so A1, M, and finally it depends on the X hats. So these are all the fields it can depend on. Okay. So I've just written these things in terms of the modes, which I'm calling the coordinates. Okay. So the other ones would be the annihilation operators. Okay, so let's write some generic states. So for example, we have e to the I k dot x hat. So that's the x hat dependence. But now you can construct states out of these things here. Now there are lots of things you can construct. For example, you can construct this one, obviously. But this is actually not the state of lowest mass squared. Because as I said, there's some objects here which have -1 here. So actually there's another state you can construct, which is just C minus 1 e to the I k dot x hat on 0. So if you do the computation here, you'll get k squared equals -1. Now there are other states you can construct with k squared equals 0. So one of them is just e to the I k dot x hat times 0. But another one you could construct is, for example, C minus 1, A1. There's another one. C minus 1, A1M, e to the I k dot x hat. Another one you could construct is C minus 1, Well, let's do this one first. C0 e to the ik dot. So you see these two states both have ghost number 1. This state has ghost number 0. There's also states you can construct with ghost number 2. So let's do some of those. So ghost number 2, you have C minus 1, C1. So it still has k squared equals 0 because you have a minus 1 and a plus 1. And you can also do C0, C minus 1, A1, M. So all of these states have k squared equals 0. And I think I've written all of them. Okay, what about k squared equals 1? Okay, obviously there are lots of them. Okay. Sorry, there's one more I forgot to write down with k squared equals 0. With we will, but in order to have a B2, good. So that would have k squared equals 1. Okay, there's one more state here that I didn't write down, which has ghost number 3. So what would that be? Yeah. So that's the last state of k squared equals 0. Okay. K squared equals 1, here's one of them, there are many more. If you had k squared equals 2, for example, you could even start with ghost number minus 1. So we see here that there are states of all ghost numbers. Okay. But at the lowest mass level, the only states you have are ghost numbers 0, 1, 2, and 3. Okay. If you go to higher mass levels, you're going to get all the ghost numbers. Okay. Yes? Sorry, so I didn't hear what you said, but let me just, so we had this equation here, and what was the question? Yes? They can only be 0 and 1. Okay, you also have, this is, let's say, from the C ghosts, and then you have another one from the B ghosts. Right, and each of them can only be 0 or 1. Any other questions? Okay, so the spectrum is more complicated, but as we'll see after the break, we'll see that the spectrum reproduces the usual super Yang-Mills states with the usual gauge symmetries, and here it'll be more clear exactly why we call these gauge transformations in these equations of motion. Okay, so are there any questions before the break? Okay, so let's take a 5-minute break. Okay, so there was something that I forgot to say, which was mentioned during the break, which is, so these are the coordinates, and the momentum which are conjugate to them are just the if this is a C ghost, it's a B ghost, and the mode number is just the opposite. So if these are the creation operators, then the annihilation operators are just, for C minus 1 would be B1, for C0 would be B0, etc. And of course you can see that all of the modes are either creation or annihilation. So for example, the annihilation goes from B1 to negative B's, and the creation starts at B2, and vice versa. Okay. Okay, so we have these states here. So let me concentrate on the states which are this state, which is tachyonic. So this has k squared equals minus 1, and these which are massless. Yes. I didn't say anything about that yet. So I'm just telling you, so the only thing I've imposed is the mass level condition, which of course is going to come from this QV equals 0. But QV equals 0 actually imposes more than that. Okay. So Q is, I think I erased Q. So for the open string, Q is just C times P plus X prime squared plus BC DC. So I can expand it in modes, of course. So you'll get a term of the type C0 times, where this means the zero mode part of P plus X prime squared. But then you could also get, for example, C minus 1 So there are all these different terms in Q. Okay? The mass shell condition comes from here. But there are other conditions coming from these. And they all have to annihilate your states. Okay? So what one finds is that this state, the only condition it has to satisfy is k squared equals minus 1. For these states, you'll find so this state is has no C's in it. Okay, so this term here, of course, it annihilates this one because C minus 1 squared is 0. But on this one, it doesn't annihilate it. So what happens is that if this, if the plus 1 mode of this does not annihilate this, then this has to be 0. Okay, but if you expand P plus X prime squared, it has a term which is just P0 times P1 plus, this would be M. So take the 0 mode from this and the plus 1 mode of this. Now the plus 1 mode of this, that never annihilates this state because these are creation operators, right? It's possible that the 0 mode here annihilates it because P0 is just the same as ddx. So for this term here to annihilate this, it implies k has to be equal 0. It has to be independent of x hat. Okay, so this state here is just a constant. So this state here, first of all, it has ghost number 0 because there's no C's, and it has to be a constant, so let's call it lambda. Okay. Okay, let's look at this state here. Well, this state here is annihilated by this because you have the C minus 1, C minus 1. So what we'll find is that this has to satisfy box on it equals 0. But there's another condition you get from the term B, C, DC in Q, which is going to relate this state with this state. So I'm not going to do the computation for you, but this is going to be an exercise. Okay. It turns out if I call this state, so this has a vector index. So I'm going to write this state in this form. So using this type of expansion here, what I'm going to do is I'm thinking of C minus 1 is just the 0, it's just C of 0, right? Because when Z is equal 0, all these other terms go away. So I'm just going to write this as C. And now A1, sorry, I already erased X. So, oh no, here it is. So when Z goes to 0, X goes to X hat. But dx goes to A1. So I can write this as dx m, where I understand this is just acting at Z equals 0. And now this is a vector, so I'm going to think of this as am of x, where the x hat dependence is just how this depends on x. So this just goes like e to the ik dot x. So this is supposed to be described by this operator here, where I understand this is acting at Z equals 0. And this object here is just independent of x, so it doesn't matter where it is. I can do the same thing here, but now this is C0, so it's dc. So this is dc. And there's no vector index here, so this is just a scalar. Let's call the scalar b. So this operator here represents this state here. This state here, I'm going to represent it by C. Now you have C1. So C1, I have to do it with two derivatives. So this is this object here, d squared C. Now it's a scalar. Let's call it, I don't know, I need a new letter, d x. Here I have C dc. Let's call this new letter E m of x times dxm. So I'm just writing these different operators here. So these are all k squared equals 0, but they have different ghost number. So these two operators have ghost number 1. This has ghost number 0. These have ghost number 2. And this has ghost number 3. So what we find is that QV equals 0 implies a relation between these. So it implies that they both satisfy box equals 0, but it also implies that dm am is equal to b. And furthermore, it implies it implies box am. So I was too quick. It turns out that the equation of motion you get from satisfying q on this is equal 0, you can get a cancellation. So the reason is because this term here would impose that box equals 0. But actually there's a C0 appearing in this term, which is b minus 1. Actually I think it's b plus 1. C0, C minus 1. This also has a C0. So you can get a cancellation between these two terms. So if the B1, if the B plus 1 here kills the C minus 1 here, you can get a cancellation between box acting on this and dm acting on this. So the correct conditions you get are these conditions here. And the gauge invariances, which are delta V equals Q omega, you find that this implies that delta AM is equal dm lambda, and delta B is equal box lambda. So you can see that it's easy to check that these gauge transformations leave these equations of motion invariant. This looks like the usual Maxwell gauge transformation. But where's the Maxwell equation of motion? So the Maxwell equation of motion comes by substituting B equals dm into here. So this implies dm of okay. So this is the way the gauge invariant version of Maxwell's equations appears in terms of these fields. Okay. So the exercise for tomorrow is to show how to get these equations and gauge transformations from these states, okay, and using Q. Okay, so you have to expand out the modes of Q and see how they act on these states. Okay. So just obviously just the ghost number 1. Okay, are there any questions? Yeah. Yeah. So we know that these fields here can be expanded near z equals 0. And if we define the states to be annihilated by all the annihilation operators, then this is a regular function. Okay. So any object which can be written in terms of the creation operators can be written in terms of these fields and derivatives of the fields. So that's what I've done here. So C minus 1 is just the value of the ghost field C at C equals 0. C0 is just the derivative of it. So if I just take ddz of this, and obviously this term drops out, and I just get C0. If I take the double derivative, I get C1, etc. So that tells me how I go from these modes to these operators here, defined at z equals 0. So similarly for dx, a1 is just the derivative of this with respect to z. Now this am of x, it's just, you should think of this as just polarization times e to the ik dot x. So, and similarly b of x is just, if I wrote it in momentum space, it would have just this e to the ik dot x dependent. So that's how I translated from these states to these. Okay, so this is a state which has a polarization because it's a vector. So let's define the polarization to be UM. Okay, so now it's a sum of these states where UM tells me the directions. Okay, now I define AM of x to be equal, and this is a polarization with momentum k. So now I just define AMX to be UMK e to the ik dot x. So this is just the polarization times the x dependence. Okay, so that's the way to relate this object once you contract it with the polarizations with this field. And similarly for this one here. Okay. Any other questions? Okay, so these are the ghost number 1. Of course, ghost number 2 is going to be a similar story. I'm not going to go through it. But these will be the antifields for the gluon. And finally, you can show that in order for this to be in the cohomology, this also has to be a constant. So this constant here turns out to be the antifield associated to this constant here. The original term was just, I called it lambda here. So this has ghost number 0, and this object here has ghost number 3. So you get the pairing of fields and antifields where ghost number 1 is paired with ghost number 2, and ghost number 0 is paired with ghost number 3. For people who know something about Yang-Mills, the 0 mode of the space-time ghost, so if you do BV quantization, delta, I mentioned delta AM is just dm of lambda here. So if lambda is constant, AM does not transform. So that constant mode of lambda is a global symmetry of the action. And that's why there's a state in the cohomology associated with it, with just this constant state. Okay, so this kind of structure is going to appear again when we do the superstring, which is why I'm introducing it here. So it's not usually done in this way, but it's one of these things which is well known, but is not it's not written up any place. Okay, so you have these states in the cohomology at ghost number 0, ghost number 1, ghost number 2, and ghost number 3. If you go to higher ghost number, even for the massive states, you'll find there's no elements in the cohomology. So though of course there are states here which have negative ghost number and ghost number bigger than 3, you find that the cohomology, when you compute the kernel of Q over the image of Q, none of these states survive. Okay, so all the physical states are ghost number 1 and ghost number 2. There is, I don't think I'll have time to discuss it, but yeah, there's this pairing when you're doing string theory of ghost number 0 with ghost number G and ghost number 3 minus G. So it comes from the fact that on a sphere the C ghost has 3 0 modes. So that's just because it's a conformal weight minus 1. Yes. Good. So, yeah, very good. So the states here, that's a good point. The states here carry a C ghost. So they are fermionic. But of course the gluon is bosonic. So this state is fermionic because of the C ghost here. But the field itself is bosonic, as you want. Okay? The antifield here, because there are 2 C ghosts, if this is fermionic, that means EM has to be fermionic. And in fact, that's what's correct. If you have antifields, they have the opposite statistics from the fields. So you could have asked this already for the particle. For the relativistic particle, remember we had phi 0 plus C phi 1. So phi 0 was bosonic, it was the usual Klein-Gordon scalar, and phi 1 was the antifield to that. But if this is bosonic, this has to be fermionic. So the antifield has the opposite statistics of the field. So, okay, so the antifields are not, they're not, when you write down the physical spectrum, you only work with the fields, you don't work with the antifield. So the antifield is, in some sense, it's some structure that you can use in order to simplify, well, so with this BV quantization, the antifields play a role. But in all the actions that you learn in quantum field theory, you set the antifields to 0. Okay, so it's something which is there, but they're not interpreted as physical states. So when people discuss the cohomology, the usual procedure is to restrict the ghost number. So of course, if you restrict the ghost number here to be ghost number 1, then the antifields you can just ignore. Okay? But if you want to work with all ghost numbers, then the antifields are there. Okay. So I know that's not a good answer, but first of all, I don't know a good answer, but also if you want to really understand how the antifields enter, you have to study this BV quantization. Are there any other questions? Okay. So the next thing I'm going to do is a spinning particle. So I won't have time to do the spinning string, but we'll do that first thing tomorrow. So if I forget to say it, tomorrow I'm going to start doing the superparticle. And the notes are, the lectures will be based on these notes, which appeared on the bulletin board, I think, last week. So for people who want paper copies, they can pick one up here. Let's see. Okay, so the starting point is very simple. We're back to the particle, so we don't have any sigma dependence. So this is called spinning particle. And what we want to do is we want to describe not a particle of spin 0, but a particle of spin 1/2. So that's why it's called spinning particle. Now, the simplest way to do this is a bit surprising. It involves anti-commuting matter fields. So, of course, we had anti-commuting ghosts before. But if you want to do this in a simple manner, what you have to introduce is an anti-commuting variable psi. So, of course, we have Pm with x dot, which satisfy the canonical commutation relations of delta Mn. And we're going to introduce an anti-commuting variable. So I guess normally there's an I people put here, which satisfies this type of relation. I'm sorry? Oh, thank you. Okay, so in this case, instead of just having the p squared constraint, we have to add an additional constraint involving the p and psi. So if we call this constraint G, and we use the canonical anti-commutation relations of the psi's, first of all, G is anti-commuting. So if it was commuting, of course, then obviously it commutes with itself. If it's anti-commuting, it doesn't have to commute with itself. I mean, it doesn't have to anti-commute with itself. So classically, G squared is 0, but because of this anti-commutation relation, you find that anti-commutation of G with G is just PM. So it just gives you the other constraint. So these are first-class constraints because they commute or anti-commute to a constraint, but it's not abelian, so it's non-abelian. How did this constraint come? You're saying why I included it? So, okay, you could have asked why I included this. So, as we said before, if I include this, then this is equivalent to an action of the type square root of x dot squared, which has something called reparameterization invariance. If you include this constraint here, you find that this, of course, is going to have some psi dependence. There are other terms here. I'm not going to write down all the terms. This action has something called super reparameterization invariance. So it has, in addition to a bosonic symmetry, it has a fermionic symmetry. So in fact, this was the first version of supersymmetry. So this is, it's called world line supersymmetry. So this fermionic constraint generates a fermionic symmetry. So that's obvious because it's a first-class constraint. So we can, of course, define the symmetry it generates just in the usual way. So delta of xm is just equal to the anti-commutator of G with xm. So you can just read it off from the commutators here. So you just get this is equal to, I guess, so if I put a so remember, here I have to put a parameter, and the parameter now is going to be fermionic because the constraint is fermionic. So let's call the parameter psi. So this is just going to be psi times psi m. So in delta Pm is, of course, 0, because Pm commutes with this, but delta psi m is not 0. So delta psi m is equal to psi times G with psi m, which is just equal to psi times Pm. And of course, you also have to vary E and chi. So this is going to be C dot. And this is going to be non-zero precisely because of this anti-commutator here. So you get the delta E is just going to be equal to psi times chi. Okay, so these are the transformations which leave the action invariant up to a total, up to a surface term. Okay. Any questions? Yes?
Is this property of the variation of time, is this dependent on the relation to the algebraic stuff?
So, yes, so G is anti-commuting, this constraint. So that's why here, sorry, this one should have been, that was my fault. That should have been anti-commutator. Any other questions? Okay, so now we can gauge fix and quantize. So we're going to gauge fix equal 1 as before, and chi equals 0. I mean, there's nothing else you can, this is anti-commuting, so the only constant we have is 0. So so in that gauge, you're just going to get x dot squared as before, plus psi dot. And then you'll get some ghosts. So you get the ghost bc dot coming from the Lagrange multiplier E. And then you get another ghost coming from this gauge symmetry. So the gauge parameter psi, the gauge parameter is fermionic, so the ghost will be bosonic. So the ghost always has the opposite statistic from the gauge parameter, so we'll call these beta and gamma. So this is ghost number +1, and this one also is ghost number +1. But this is commuting, and this is anti-commuting. Okay, so this is the gauge fixed action. And then the BRST operator is just going to be C times P squared plus gamma times the fermionic constraint. And then finally, because of this algebra here, you get a term gamma squared B. Okay, so remember gamma, each G comes with a gamma. Each G is related to gamma, and this is the constraint to generate. So that means that this comes from the term CCB F. It's just that some of these are gammas and some of these are B's. Okay. Okay, so it's easy to show that Q squared equals 0, for example. Just using this algebra for the G's and the usual commutation relations and anti-commutation relations. Any questions? Okay, so now we want to get the spectrum. So we have V, which is going to be a function, okay, of the C's and of the X's and of the psi's. Oh, and also the gammas. Sorry, I forgot the gammas. C's and gammas. So we'll think of beta and B as being the momentum. But the psi's cannot be all considered as coordinates because the psi's anti-commute with themselves. So you should really think of half of the psi's as being coordinates and half as being momenta. If you want to do this in a covariant way, so of course you have to choose half of them. You have to break the SO, in this case SO10. So when we do the string, we'll find that the critical dimension is 10. So you have to break the Lorentz symmetry if you want to choose half of them to be coordinates and half the momentum. We don't want to do that. So what we're going to do is we're going to realize that this algebra here is the same as the algebra of gamma matrices. So unfortunately, gamma is also used here, but I guess normally we put a 2 here. So this is if I divide by square root of 2, these are how gamma matrices act on spinor. So gamma matrices are just matrices, which they're n by n matrices, where n is the dimension of the spinor representation. Okay? It will turn out in 10 dimensions. These are 32 by 32 matrices. But we'll see more about this later, so I don't want to go into too much detail about the gamma matrices for now. So what that means is that you can describe this as a function of just C gamma and x, not as a function of psi, but we're now, this is a spinor. So maybe I should do it like this. And where the definition of psi m acting on V alpha is just defined to be the gamma matrix, which has these spinor indices contracted with V beta. So in this case, alpha equals 1 to 32. So these gamma matrices are 32 by 32 matrices. And acting with psi on this spinor representation is the same thing as acting with the gamma matrix. And that, okay, divided by square root of 2. That trivially satisfies this identity. Because if you act twice with psi and anti-commute, you'll just get the same relation as if you do with the gamma matrices. So this is a covariant way of treating these psi's, okay? Of course, there are non-covariant ways by treating half of them to be creation and half to be annihilation. And what you'll get is you'll get a state. So let's just to tell you what the relation is. Let's suppose we chose psi 1 plus I psi 2 to be creation operators, and psi 1 minus I psi 2 to so that's a certain choice. Yes? Okay, so psi satisfies the anti-commutation relations of this type, which are the same anti-commutation relations of the gamma matrices. So I'm looking for some state which transforms, which psi acts like an operator on that state. So because they satisfy the same relations, one can argue that the representation is just a spinorial representation, where psi acts just like a gamma matrix on that spinorial representation. So that's how I got this spinor here. Now, I can derive that in a more straightforward way, but non-covariant way, by choosing half of these to be creation and half to be annihilation, or half to be coordinates and half to be momentum. Now that choice is going to break my symmetry. So this choice here breaks SO10. So let's suppose we rotate from 9,1 to 10 dimensions. This chooses 5 complex psi's to be creation and 5 to be annihilation. So this breaks SO10 down to U5. So there's a subgroup of SO10 which preserves this choice, and that's this U5 subgroup. Now, this is going to come back later, so I might as well spend a little time doing it now. This choice of creation and annihilation chooses a single state. So there's a single state which is annihilated by these psi's, and I'm going to label that state with a notation minus, 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 minus. Why? Because it's annihilated by all of these. So the first minus comes because it's annihilated by psi 1 minus psi 2. The second one comes because it's annihilated by psi 3 minus I psi 4, etc. Okay? So that's the ground state. Now, if I hit the ground state with one of these, obviously I get 0. But now suppose I hit it with psi 1 plus I psi 2. That takes it to a different state. So psi 1 plus I psi 2 acting on this state is no longer annihilated by psi 1 minus I psi 2, because psi 1 minus I psi 2 doesn't anticommute with this. So this state I will call plus minus 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 minus, because it's annihilated now by, still annihilated by these, but it's no longer annihilated by psi 1 minus I psi 2. It's annihilated by psi 1 plus I psi 2. Because if I hit this with psi 1 plus I psi 2, I get 0, because this thing squared is 0. So using this method, I can get all these states. So I start with 0 minus 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 minus, 0 plus, minus minus minus. I can get to all the different states. So in the end, I get all my states are described by either plus or minus, plus or minus. Plus. So there are 32 different states, because I have plus or minus. I have 5 different plus or minuses. So I have 2 to the 5 states. So there are 32 such states, and these are precisely the 32 components of a spinor in 10 dimensions. Okay? So in this description here, I have a ground state, which is a single state, and then I get the other states by hitting with psis. In this description here, I did it all at once. Okay? I have V alpha, and the alpha just tells me which of the psis annihilated. Okay? So it's the same notation. It's just this notation is something that looks more covariant to you. Okay? This notation is only manifestly covariant under the U5 subgroup of SO10. Whereas this notation is, I mean, if you interpret the alpha as just some 32 component spinor representation, this is manifestly SO10 covariant. Okay. Sorry? Okay, so we've Wick so we're in 10 dimensions because we're doing the superstring. And I Wick rotated to go to Euclidean 10 dimensions. If I didn't Wick rotate, then instead of this one being psi 9 plus I psi 10, there'd be no I here. And then it would be a different subgroup, which is more complicated to describe. But okay, so I'll do it for you. Okay, so you have SO91. So this is, of course, the Minkowski space. And now one can look at the subgroups of that. So there's obviously a U4 subgroup, which is a subgroup of SO8. So that's the little group you were mentioning. But this has 16 generators. There's still 9 other generators that preserve this split. So those 9 other generators are the ones that rotate psi 9 plus psi 10 into these. So it turns out not to be a group. So you have 25 generators, but it's the 9 generators don't transform together with the U4 to give you a group structure. They transform, I don't know what it's called. It's some ISO4, something like that. So I don't know the right word for it, but do you know the right word for it? SO or SU? Okay. Okay, so I in any case, it has 25 generators. So it's just that they don't together form a group. I mean, they don't satisfy the properties of a subgroup. Yes? Yes. So the psi m has the same, it's a vector just like the p's. So even though it's anti-commuting, it's a space-time vector. Another question? Okay, so we have this representation, and now we just have to look at the states. So I'll start with this tomorrow, but let me just say the answer, and then. So what we're going to find is that V alpha has a term phi alpha, which has no C or gamma dependence. So let's call it 0. And then you have terms like C, phi 1. And then you can also have gamma. And then you can have C gamma. So I'm just writing all the terms. You can have, of course, either 0 or 1c, but you can have an infinite number of gammas. So this goes on forever, because you can have gamma squared, gamma cubed, gamma fourth, etc. What you'll find is that phi 0 describes spin 1/2. So it will have to satisfy the Dirac equation, the massless Dirac equation, d slash of phi 0 equals 0. And then what you'll find is that these two together also define, when you go to the cohomology, you'll find that this also satisfies massless Dirac equation, and you keep going. So you'll find that you actually get not just 2 copies, you get an infinite number of copies. So with each of these ghost numbers, you're going to get another copy. So this will be identified as the physical state, and these copies, as we'll see when we do the string also, to describe space-time fermion. So this is, of course, the space-time fermion. In this type of language is a mess. Okay, so this is the first place where the mess comes in. You're getting infinite copies of the states. When we do the string, you'll see in more detail what gets messy. So this is related to the fact that in this formalism, it's difficult to describe space-time fermions. So this is why, one of the reasons why it's convenient to go to this Green-Schwarz or pure spinor formalism. In some sense, because in this formalism, the anti-commuting variable here is a space-time vector, which is a little bit counterintuitive. Normally you would expect the space-time vectors to be commuting. In this Green-Schwarz or pure spinor version of the superstring, the anti-commuting variables are space-time spinors. So it's more natural, and it will turn out to resolve these difficulties here. Okay, so next lecture we'll see more about this, and then we'll go to the spinning string and then the superstring. So there are notes here, as I said, so if you want a paper version of the things I'll describe in the next lectures, you can get a copy here. Okay, so I'll stop there.